Today what we will do is we will continue where we left yesterday, and there's some addition to that what we were doing yesterday. Now discussing about these governing equations, first observation is that it's a coupled system of non-linear partial differential equation, and to date no general analytical solution exists for them. We have said this a number of times that there is no analytical solution for these equations. Now when we examine these Navier-Stokes equations, we have 5 equations, but there are 6 unknowns. One is rho, p, u, v, w and e. This is a set of 5 equations, 6 unknowns. Hence we need one more equation to solve this set of equations. That's very clear. Number of equations and number of unknowns should be same. So in aerodynamics, what we do, we can use this assumption for the gas is a perfect gas, that air, if we are using air can be taken as a perfect gas, or if any gas temperatures are higher, pressures are not very high, gases behave like P is equal to rho RT. That means pressure can be replaced by temperature. But then what we have done is we have replaced pressure by temperature. So we are back to same place. 6 unknowns. Okay. Now then what we do, so what we have done is that we have actually introduced a 7th field variable, which is temperature, and okay, we have equation P is equal to rho RT, so you can say there are 6 only. Okay, but then you have another equation which is the 7th equation, that is E is a function of temperature and volume. Now E is specific internal energy. We know that U is a function of temperature comma volume. So we can take this equation. Now so volume is nothing but, this is a specific volume, so it is nothing but it is your inverse of density, right? So what we are doing is basically E we are writing in terms of T. So here you find that P and T, P and E both are written in terms of T. So basically if you use this equation, you reduce one variable. So you come to 5. From 6 you come to 5. So from 6 you went to 7 by adding T, but then you removed P, you come to 6, and then you remove E also, you come to 5 back. Okay. Now normally we consider the gas to be calorically perfect gas, that is E equal to CVT, where CV is a constant. So in most of the cases the internal energy will not be taken as function of density, although it is a specific volume or density, but in limiting case you can take that. And then this equation is called calorific equation of state, caloric equation of state, but anyway, so this is how you deal with it. So yesterday what we were doing, that we had replaced all tau with derivatives of u, v and w, and put lambda and mu there, okay, which are the properties of fluid. Now here what we are doing is we are removing P and E, replacing with them with T, okay, and we are introducing what is P is equal to rho RT. One is the gas equation, and the second we are using is E is equal to CVT. So we are adding CV also there. Again, CV is a property of gas, right? So property which is constant, almost a constant, okay. So what is, even temperature is a property, density is a property, right, thermodynamic property, but CV is a constant, mu also, either it is a constant or function of temperature, etc., it can be taken up. So this is how it satisfy your 5 equation, 5 unknowns, and we can proceed from here. There is another you can say that historically how these equations have been named. So something about the history. Now originally what used to happen, the momentum equation for viscous flow, that means in which mu is there or tau is there existing, okay, momentum equations, they were called Navier-Stokes equation. That was the originality. But now what is happening in modern CFD literature, entire system of flow equation for a solution of viscous flow, okay, which include continuity equation, momentum equation and energy equation, they are termed as Navier-Stokes equation. Originally Navier-Stokes equation was only momentum equation, but now all the 5 are taken together and called Navier-Stokes. And there was a scientist called Euler. He derived only continuity equation and momentum equation in 1753. Another 100 years back. So we have now 280 years back. Euler derived only the continuity and momentum equation in 1753. So strictly speaking, only the continuity equation and momentum equation shall be labeled as Euler equation. However, in modern CFD literature, entire system of flow equation for an inviscid flow is termed Euler's equation. Okay, so the same equation. So historically they are different. Historically Euler did continuity and momentum equation, and probably for non-viscous flow. Momentum equation for viscous flow were done by Navier-Stokes. But now Navier-Stokes equation means all the 5 equations. If it is viscous flow, it is Navier-Stokes. If it is non-viscous inviscid flow, it is called Euler's equation. Okay, so this is something to do with the history. And now in this article what we are doing is, all these Navier-Stokes equation we are writing in generic form. Okay, what does that mean? Actually, the whole process is that we are going to show that all the equations are similar. They can be replaced by similar equation, which is called a generic equation. So all the 5 equations can be replaced by a not single equation, but similar equation for all of them. Now what will be the advantage of that? It is so what we are going to show that all Navier-Stokes equations can be represented by a common generic equation. The advantage would be that it will help us in better appreciation of the conservation equation. Now this generic equation has a physical you can say meaning to all the terms, so that we can understand what is happening in each equation. That is one benefit. The second thing is you can develop a common code for the solution of equations. You just have to replace the variable, and because the equations are same, what will happen? The two equations will be different from each other by, in some equation some term will be there, in other case some other term will be there. So some other term will be 0, right? The coefficients will be different, the parameters will be different, but the equation will be same. This is what will happen. So this is what we are trying to do. Now, so one thing you will note that all the equations which are governing equation of CFD, they are basically conservation equation. We know that. Okay. And they are conservation of mass, momentum and energy. That means there is a similarity between all of them. Although they are showing all of them as different equation, but there is a similarity that all of them are conservation equation. What is changing is the quantity, the physical quantity. At one place it is mass, the second place it is momentum, at the third place it is energy. Okay. Now, what we can do is that we can write these conservation equations such that there are different terms in it, and these terms are accumulation, advection, diffusion and source terms. So whole equation can be divided into 4 terms. One of them will be accumulation, the second is advection, third is diffusion and the fourth is source terms. Right? Now if we look at them, you can take it like this. This is the control volume, right? Now accumulation means something is being collected here. Accumulation, accumulate, that means something is added here. So if the mass is increasing in it, that we are saying accumulation, or mass is depleting from here, so it is minus of accumulation. Then source means it is generation. So the quantity is being generated within or it is being consumed. Okay. Then the same quantity can flow in through the walls by diffusion, right? And same quantity can go out from the control volume by advection. Now you should remember what is the difference between these two, diffusion and advection. Diffusion takes place across a impermeable boundary. This boundary is impermeable, impervious. So mass cannot enter here. What is entering in? Energy can enter in. Momentum can enter in, even without entering the mass. So diffusion term actually represent the physical quantity entering into the control volume or going out of the control volume without mass going in or coming out. But on the other side, advection is different. In advection, physical quantity is going in with the mass, with the fluid entering in. So if there is no fluid entering in, there is no advection. So either the fluid should be going in or the fluid should be coming out. And because this fluid element will be carrying that physical quantity, so it will be taking in that physical quantity or taking it out. Any of these things will happen. Okay, so this is the basically difference between. So diffusion, the same physical quantity is entering in without mass going in. Advection is the same physical quantity going in or out with the mass. Okay, now if you put all this, you can say whatever is the accumulation within will be equal to diffusion. Diffusion is going in, source which is generating within, and advection which is going out. Okay, so you can rewrite this equation. You can bring advection on this side, and you can say accumulation plus advection is equal to diffusion plus source. So accumulation is, that is, the physical quantity is getting increased within the control volume. Advection is that much is going out, right? And diffusion is what is coming in, source is what is being generated in. So this is the physical interpretation of this. So now what we are going to do is that we can show all the equations in terms of these four quantities. At the end of this article, you will find that all the four equations can be written like this. So we will know that which is the accumulation term here, which is the advection term here, which is the diffusion term here, and which is the source term here. Okay, and then we can clearly know that which is absent, whether the accumulation is absent, whether the source is absent, whether the advection is absent or diffusion is absent, we will clearly know. So we will know physically what is happening there. So it will help us correlate with the thing. Okay. Now let us go about doing it. We will do it using generic parameters. So first we'll do it for a generic parameter, and those generic parameter we are using at phi and psi. These are the two parameters we are using. Okay. Now what we will be doing is, in the end we will be showing that these generic parameters can be replaced by the parameters which are there in the generic equations, in the governing equations, sorry. Okay. So what does that mean? That the same generic equation can be written as momentum equation, mass equation, and energy equation. Okay. So first we should know what is the difference between phi and psi. Now psi is actually, if you define for a volume, so you have some volume here which is VL. Okay, you can have a volume like this also, anyway, any volume you can have. Take the value of phi at all the points, integrate over volume, you will get psi. So psi is nothing but phi into volume. Okay. Now if you take the limiting case that VL approaches to 0, what is happening is, you will know that psi is equal to phi into delta VL. This delta VL, you can make it approach to 0. Now the psi and phi at a point are correlated. In the above equation, they are correlated for a finite volume. Here they are related for infinitesimal volume. So at a point, psi is, or you can say, in other words, you can say that phi is nothing but psi per unit volume. That is what you can say. So there is a physical quantity. If you find the physical quantity per unit volume, that becomes phi. So psi per unit volume is equal to phi. So this is how you can write. You can also write it. This is a better way of writing psi divided by delta VL. Now, what are the examples? You can take the example. If suppose psi is equal to mass, phi will be equal to rho. Well, if psi is equal to mass into velocity, that is the momentum, phi will become rho into velocity. Okay? So we are here. If psi is equal to momentum, phi will become rho v, and similarly, if psi is equal to energy, thermal energy, mCVT, phi will become energy density. Okay, and if we talk about psi as total energy, CVT plus half V square. So kinetic energy also we are adding here. This is the kinetic energy, and this is your thermal energy. We are adding the both, so it becomes a total energy. Then phi will become a specific total energy. So phi is, you can say, in one case it is density, in the second case it is specific momentum, third case is a specific internal energy, and in the fourth case it is specific total energy. Okay, now we talk about accumulation term, and we'll just explain what it is. Okay. So we consider a volume. This is delta VL, same volume here, state 1 and state 2. At one point of time it is this, at the second point of, it's not moving, it's only because I have to show it's a control volume, so it's fixed. Okay, not moving. Because I have to show two, so I have to separate them. Now, if you write del phi by del t is equal to phi 2 minus phi 1 divided by delta t, where delta t approaches to 0. Normal. Now, what you can do, same thing, you can multiply it by delta VL up and down, divide by delta VL, and put this limit also equal to 0. So you have, so now what is happening is, you are talking about a point. Here you are talking about, you can say it's a general mathematical equation. Del phi by del t is equal to phi 2 minus phi 1 by delta t, where what we are talking about, we don't know here. It's just a derivative, how to find the derivative. But when you come here, what is telling is that d phi by dt at a point, what it is. So it will be phi 2 del phi 2 minus phi 2 del VL minus phi 1 del VL divided by delta VL delta T. Okay. Now what does that mean? It is telling us change in a physical quantity stored in the control volume. So we have a control volume where final value of that physical quantity is psi 2 and initial value is psi 1. Right? Psi is volume into phi. Okay. So what is stored is psi 2 and what is originally there, psi 1, difference between the two. So you can write it like this. What you are doing here is you are replacing this term and this term by psi 2 and psi 1. This is you are replacing. Okay. So this is what it becomes. Okay. Now here what we are doing is same thing. What we are assuming? Yes. Psi is nothing but phi into delta VL when delta VL is approaching to 0. Okay. So we write it like this. Again same thing, it was not required. Okay, then you take out delta VL. This VL is not changing, it's a control volume, so you can take it out of the derivative. Okay, so this is the equation we get. Now what is this del phi by del t? This is, you can read from here what it is, rate of psi accumulating in the control volume per unit control volume. So del phi by del t is what? Del psi by del t per unit volume. So this is the physical quantity which we know. This is phi is a physical quantity which is a specific of the same. Okay. So although okay, so what we have here is del phi by del t is telling us the rate of psi accumulating within the control volume per unit control volume. Okay. Now if you have rho here, del rho by del t, psi is rho multiply, psi is phi multiplied by delta VL. So this will become m. So this del rho by del t is nothing but rate of mass accumulating in control volume per unit control volume. So wherever you are getting this term del rho by del t, that tells you how much of mass is accumulating in the control volume per unit control volume per unit time. Okay. Now if you have this rho v, so this is your phi, so psi will be equal to mv. So this tells you the rate of momentum mv accumulating in the control volume per unit control volume. At what rate volume is accumulating inside. Okay. Similarly, you can take this. If this is your phi, so this is your psi. So it is telling us that what is the rate of energy accumulating in the control volume per unit control volume, per unit volume of the control volume. Okay, so this is how you can interpret all of them. So you have these three: del rho by del T, del rho V by del T, and del rho CV T by del T. Okay, each one. Now we talk about advection term, and we are trying to interpret this. What does it mean? Now again we will consider a control volume delta VL, and you can write this simple derivative as del U phi by del X is equal to this much. This is the definition of the derivative. What does it mean? We don't know. Now we are trying to give a meaning to it. So you can always write like this: del U by del phi by del X will be equal to, you multiply this whole thing by del Y by del Z, divide by del Y by del Z. Okay. So U2 phi 2 minus U1 phi 1. Only thing what you have done is del X, del Y, del Z, they are approaching to 0. Okay. Now this is, you have converted this into delta VL. Same equation you have converted to delta VL. Okay. Now you know this term U2 multiplied by del Y del Z. This is the amount of fluid flowing out from the right phase per unit time. Volume. Look at this diagram. This Q2 is equal to U2 del Y del Z, and Q1 here, Q1 dot is equal to U1 del Y del Z. So Q1 dot and Q2 dot are telling you the volume of the fluid which is entering in per unit time or going out per unit time. Okay. Now you come here. So phi 2 into Q2 dot minus phi 1 into Q1 dot. Okay. So where you know Q2 dot is the rate of volume of the fluid leaving the control volume from the right side, and Q1 dot is the rate of volume of fluid entering the control volume from the left side. Okay. Now this thing, this term, this is nothing but psi 2 dot, and this is nothing but psi 1 dot, because when you multiply it by phi 1 with volume, you get psi 1 multiplied psi 2 phi 2 by volume, you get phi 2. Okay. So this is nothing but psi x2 dot minus psi x1 dot divided by delta VL. Okay. So you can interpret what is this, u into phi. Now you are finding the derivative of u into phi. Earlier you found the derivative phi with, we had talked about earlier del phi by del t. Now we are talking about del u phi by del t. Okay, what does that mean? It is equivalent to rate of psi flowing out of the control volume in x direction per unit volume of the control volume. This is telling you what? How much of psi is flowing out net, because something is coming in, something is going out. So how much of psi is flowing out per unit volume of the control volume per unit time. Okay, and in x direction only. Now you can similarly say that del v phi will be psi flowing out of the control volume in y direction per unit volume of the control volume. And w phi derivative will be equal to rate of psi flowing out of the control volume in z direction per unit volume of the control volume. You can combine all these three, you get this. These are the three terms we talked about. And these three terms are equivalent to psi flowing out in x direction, flowing out in y direction, flowing out in z direction. What does that mean? If you combine them, it is psi flowing out from any surface. The overall psi flowing out. Okay. So thus psi 2 is what? Rate of psi flowing out of the control volume along with mass. And this is flowing out with mass, or you can say with volume. Okay. Psi 1 is the rate of psi flowing into the control volume along with mass. Okay. Because if u is 0, u, v and w are 0, it's all will be 0. Nothing is going in, nothing is coming out. It's because of u, if we talk only in direction x, it's because of u, volume is going in, volume is going out. Okay. So divergence of v phi. Now you recall that this term we have come across. Divergence of v into phi is actually net rate of psi flowing out of the control volume from all the surfaces along with mass per unit volume of the control volume. We talk about these all the terms because they are important, and similarly in the above equations also you can interpret. Why I am saying net rate? Because something is going in, something is going out. The difference between the two is the net rate. Why I am saying net rate? Because something is going out, something is coming in. The difference of the two is psi. Psi is the physical quantity we term. It was mass, it was momentum, and it was energy. Okay. Flowing out of the control volume from all the surfaces. So we have to take all the direction x, y and z. Okay. So they are entering from all the direction, they are going out from all the directions. So you have to take, because otherwise we have taken x, y and z. Phi x, psi y and psi z. We have added up all of them, all the three components, direction wise. Along with mass. This quantity is entering in or going out because of the mass, because the fluid is flowing in or out, and that is why it is called advection. Something like convection. Okay. Here the name is used advection. It is same as convection. If you talk about heat transfer in convection, it is because of the flow of the fluid that convection takes place. Okay. So the heat flowing because of the flow of the material or the fluid. Of course, in solid there will not be any flow of material, so there will not be any convection. Convection takes place where? In the fluid only. Okay. Per unit volume of the control volume, that is clear. So what we can say, where psi is nothing but this. Okay. Or you can say phi is nothing but psi divided by delta VL, whichever way you feel like writing it. Okay. Now we take the examples of advection. Now if you are talking about phi as rho u, okay, phi as rho u, then psi will become rho u into delta L, that will become mu. Earlier our psi and phi, they were arbitrary, generic. Now your phi is rho u, so psi will be mu. Okay. So what does this mean? If you write this equation, it will be equivalent to this, right? And if this is the case, you will multiply this by psi will be equal to m mu. Psi is equal to this much. This is phi, so this is equal to psi. Now what does this equation represent? Net rate of momentum in x direction flowing out of the control volume from all the surfaces along with mass per unit volume of the control volume. Okay. If you take phi as rho e, or in other words rho as CVT, your psi becomes equal to mCVT multiplied by volume. So what will be this equation? This will be equation net rate of flow of this term. This is the thermal energy flowing out of the control volume from all the surfaces along with mass per unit volume of the control volume. Okay. So this is how it goes about. So what we have done is actually we have seen first thing that all the equations of Navier-Stokes, they are equations of conservation, and the physical quantity involved are mass, momentum and energy, and physically they can be broken into four terms. One is called accumulation, the second is called source, diffusion and advection. Now then what we are doing is we are showing that if you have phi as one quantity and psi, then psi we are taking as another quantity, where phi is a density of psi, or you can say per unit volume of psi is equal to phi. And if you define your parameters like that, then we have talked about del phi by del t and del u phi by del t when you multiply it with velocity. Okay, and accordingly we have found that what is happening in the two cases. So when it is only del phi by del t, it talks about accumulation. When it is u multiplied by, so this term del phi by del t is actually talking about accumulation term. But when you talk about del u phi by del t, it is talking about advection term. Okay. Now we will, after this, we will talk about diffusion term. So we will stop here, and diffusion term we will do in the next class. Okay.